In this video, we're going to talk about shear moment diagrams. Shear moment diagrams are a very important skill that you're going to need to know in statics here. This is fundamental. We're going to introduce it in statics. You are going to be then continuing on and using this when you get to mechanics of materials or deformable body mechanics, and you're going to really need to know this. This is a very important skill, so I wanted to do a little video to go over some of the basics to supplement some of the information in the book. Now, when we do shear moment diagrams, there's really two main ways to do it. And I'm going to cover the first way, which is basically coming up with the equations for the shear and moment components to create those diagrams. Now, to be able to do shear moment diagrams, you're going to need to understand how to do internal forces. So our internal forces, you're going to need to take a beam that is supported, it has its load conditions on it, and then be able to take it, and if we're looking at some point, we need to be able to cut this beam, and then we need to be able to split this up so that we can get our reaction force at our support. We can then have our internal forces, our normal, our shear, V, and our moment, M, at that face. So we need to be able to go in and calculate up V, N, and M in this condition. So if you don't know how to do that, go back, look at the internal forces portion of the book, watch a video that might help you out. Once you know how to do that internal forces, we're going to make the shear moment diagram. Now, what is the shear moment diagram? At this point, when we calculate the internal forces at this point, we're calculating the shear and the moment. In this case, most of the time we're going to neglect this normal force on the shear the normal force on the beam, because most of our loading is going to be perpendicular to the beam. It's not going to be in the axis of the beam. So we're going to neglect the N here. Although we did calculate it for most of the internal forces, we're going to neglect that for our shear moment diagrams at this point, because we're just going to be looking at shear and the moment. Now, when we create the shear moment diagrams, what we're going to do is we're going to create a diagram that shows the shear along the entire length of this entire beam, and a moment diagram that's going to list all the moments along this entire beam. So really what we can do is, if we think about it, we really are taking and calculating the internal forces at every point along this beam. Well, we're not going to actually cut it and calculate it for each section or each point along that beam. We're going to split these beams up into specific sections, and once we split it up into different sections, then we can get the equations for the shear and moment in those sections, and then it'll make it a lot easier. So we're not calculating a bunch of them, we're just calculating a couple of them. Now, the guidance that we're going to do when we break up our beam, and I'm going to use this for our example. This is a simply supported beam with a concentrated load. I'm going to call this right in the middle of the beam. What we're looking for are sections, or we're going to break it up into sections where we have point loads or point reactions. Basically, point loads or forces. That could be a reaction, or that could be applied load. Those are going to be the boundaries of our sections. We're also going to be looking at distributed loads. Now, the distributed loads, this problem doesn't have it. We're going to cover that in a little bit. But where we have distributed loads that have an abrupt change, we need to make those a new section also. If it doesn't make sense, I wanted to kind of lay that out there for you right now. If it's not super clear, I will do some examples here in just a little bit. But basically, we're going to split this up. So this beam is going to be split up into two sections. It's going to be split up into this section because we have a point load here, and then we have another section there. So we can, in this region right here, there are no point loads. So we're going to treat this as one section. So we're going to call that section 1. This one we're going to call section 2, and that will be our entire beam. Now, the other thing that we need to do is we need to give a coordinate system, and in this case I'm going to call this X. So we're going to calculate everything from the left hand side of our beam. So that will at least get us so that we can have our shear moment diagrams. It helps with the equations, and if you just put that out there, just like we do with all of our systems, we throw on our arbitrary coordinate systems and define it. Just a good habit to get into. Now, if we are going to do this beam, I'm going to redraw this here, and we're going to have our beam. So here, let me just redraw this real quick. So we have our lever, we've got our pin, we've got our roller, we've got our load P. This beam has an overall length of L. This is going to be L over 2. This is going to be L over 2 from here to there. Let's do that. So first thing we need to do, always with our beams, we need to calculate our reaction forces or draw our free body diagram. So in this case, our free body diagram is going to be this. We're going to have P here, our load. We're going to have our reactions at the ends. We need to calculate these reaction forces. So in this case, this problem is very easy. We can calculate it almost by just looking at it. And we know that since this is in the center, our reaction forces are going to be P over 2 at both ends. Now, if it's not intuitive, you're going to have to go through, use your static equilibrium equations, calculate up your reaction forces. And you want to do that before you start this problem. So at this point, now we have identified that we have two different sections that we're going to look at. So we're going to look at section 1 first. And what we're going to do is I'm going to draw this down here. And the way that you want to draw your shear moment diagrams is you always want to line them up. So I'm going to draw, this is going to be our shear. Okay, so we've got the end lines up with the end. This end lines up with the end. P is going to line up right here. Okay, so it's all going to line up, and this is going to be shear. Above the axis is positive, below the axis is negative. And then what I'm going to do is I'm going to draw the moment diagram right below it. Again, I'm going to line it up exactly. So I've got this. So this lines up, RP lines up right in the center. And this is going to be the moment, positive, negative there. So that's really how I want you guys to do it. I want you to show your free body diagram. I want you to show your loadings on here, your shear, and your moment. Make sure everything lines up. It is going to make it so much easier on you if you do that. If you don't, again, it's just going to make it a lot harder. So first thing we want to do is look at section 1. So what we want to do is we're going to look at the internal forces in this section. So we're going to break this at some point, just like we did with our calculating our internal forces. But now at this break, we're going to call that distance X from the left-hand side. So that has at some point X there. So if we redraw this, we have our cut section, we have our reaction force, P over 2, we have our shear, we have our moment. Okay, now I've drawn those both in the positive direction so that we make it easy on ourselves calculating this up. And then we also have our distance X in there. So we have that in there. So now what we want to do is calculate up the shear and moment. Now if we look at this, we can say sum of the forces in the y direction is equal to 0, and that's going to give us P over 2 minus RV equals 0, or V is going to be equal to P over 2. This is our equation for our shear. So shear in section 1, it doesn't matter what X is, because X is not in our equation here, but that is going to define our shear. So now we can come down to our shear diagram, and this is a positive shear. So we can come up here, this is P over 2, and our shear is going to be positive P over 2, all the way from the left-hand side, all the way to our point where we have our load put on there, or point P. So that is our shear. So that's that so far. Now what we're going to do is continue our, well, let's do this. Let's go and calculate up our moment in section 1 next. So to calculate up our moment, I'm going to do the moment right about this point here, and I'm going to call that point O. So some of the moments about point O, and I will call this direction positive, and that's going to be equal to 0. So what do we have? We've got our moment, that is our M, And then we have the V, because it's going through point O, does not create a moment. We have our P over 2, and that is at distance x, and that is going to be creating a negative moment. So this is going to be minus P over 2 times x equals 0. So we can rearrange this. We can find that m is equal to P over 2 times x. P over 2 times x. So there is the equation for the moment in section 1. So now what does that mean? If we look at this, the equation, we can see that this is a linear relationship varying with x. So when x is equal to 0 on our left side, moment is going to be equal to 0. Now it's going to go all the way to where x is going to be L over 2. So if we put in at L over 2, m is going to be equal to P over 2 times L over 2, or that's going to be equal to PL over 4. So the moment at point P, or at the middle of the beam, is going to be PL over 4. So that's going to be right here. So I'm going to mark this, and this is going to be PL over 4, and it's going to start off at 0, and it's going to go up to that point, and we know it's a linear equation, so it's going to be a straight line. So now we can draw that in there. So there is our, and we know it's positive also. The thing is it's positive there. Now what we can do is really we need to start taking a look at section 2. Well, if we look here on our shear, one of the things that we need to take into account is that force P is a negative, or is a shear. It's creating a shear in there. And because this force is going downward, we're going to be going down a P value. Okay, so basically from here, which is P over 2, it's going to go all the way down. So this distance here has a value of P. So P over 2 minus P takes us all the way down to minus P over 2. Minus P over 2. And in this case, one of the things that we can do is we can go through and actually cut the beam on the other side, or in section 2 over here now. So what we could do is, just like with our internal forces, if we cut the beam, we can use this side, or we can use this side. And if we use this side here, we have P, and we have this other reaction force that we're going to have to deal with. It's going to make the equations a little bit harder to deal with. So what I'm going to do is I'm going to use this right hand side. So basically this is this section here where we have P over 2. Oops, I'm right close to the bottom. I'm going to get all the way up there for you. And then we're going to use the shear. Okay, so we have V, and then we have our M. Again, I've drawn that because we're on the right-hand side. We need to draw our moment and our shear directions differently, or in the opposite direction, to keep them positive. And now the only other thing that we don't have here is we need to know what this distance is. Well, X is still from this left-hand side. So this point is X. So the length of this is really the overall length of the beam minus this distance X. So this is L minus X. That's that distance right there. Okay, so the length of our side over there is L over X. So in this case, we can go through, do everything again. Some of the forces in the y direction is equal to 0. And in this case, we can look at this and we can say we have a positive V plus P over 2 equals 0. Shear is equal to negative P over 2. So in section 2, our shear is negative P over 2. Well, if we look at this, we came down. We are already at negative P over 2. And it is going to come all the way over. And our reaction force goes up P over 2. So we end back at 0. The very ends of those beams should actually be at 0. So now this is our shear diagram for this beam right there. That's it. I'm just going to shade it just a little bit so you can see it a little bit better. Now, the other thing that we need to do is calculate up our moment. So our moment here, our moment's going to look a little bit more confusing because of this term, L minus X. Okay. And let's see, I am running out of space here, but I want to keep it on this page. So I'm going to go up and use this space right up here. So I'm going to do sum of the moments about point O. This is going to be point O again right here. And that's going to be equal to 0. So, and this time what I'm going to do is I will say clockwise is positive again, or counterclockwise, I should say. And so what we're going to have is minus m, and then p over 2 is going to create a positive moment. So that is going to be a positive p over 2 times the distance, which is L minus x there. And that's going to be equal to 0. So we can rearrange this and we get m is equal to p over 2 times L minus x. Okay, so there is our equation. So this is the equation for the line of the moment on the right hand side, or in section 2. Now if we take a look at this, really section 2 is from L over 2. Okay, so from this point x equals L over 2, which is the very center of the beam, to x equals L. And if we plug in here, let's take a look at x equals L. What is this equal to? So at x equals L, we can plug L into here. So we have m is equal to p over 2 times L minus L. L minus L is going to be 0. So that means the moment is equal to 0 at x equals L. So at this point, at the very end, it's going to be equal to 0. At x equals L over 2, what is the moment equal to? So we need to plug that in here. So moment is equal to p over 2 times L minus L over 2. So L minus L over 2 is L over 2. So we get PL over 4. PL over 4. Well, that's where we already are. We're at PL over 4. And if we look at this equation, this is a linear equation. And if we could write this out, we have a negative slope. And this is essentially going to turn into a straight line from there all the way down. So here is our moment right here. So there's our moment diagram. So we have our shear, we have our moment. The other things that you need to make sure that you put on there. What is, label the moments or label the shear. So we have each of the points here, and then we need to label the maximum or the values for the moments. And we are, since there is no negative moments, it's only at 0.0. So or the moment, the minimum moment is 0. And we only have positive moments. So this is how we would do a shear moment diagram with a single point force. And if we had more forces on here, so let's say we had 2 forces, we would now have 3 different sections. We would have to do this in all 3 sections on there. But that's how we do it. Hopefully that gives you a good idea on how to set this up. Main thing is set this up, draw it graphically, so it's very clear for you. That'll definitely help you out in the future.